Good morning, further maths people. Today, very exciting, we are going to build up to really big result. One of the most important results, I think, in number theory, to do with prime numbers, as much of number theory is, but it helps with cryptography, dealing with huge primes, well, huge numbers, and do we know if it's a prime or not? So to help us to discover that, to start with today, I want us to do a little investigation into looking at the residues of powers. So in this first table here, which you might want to print off, or you can just kind of scribble down, I've got powers of 2 up to power of 7, and I want you to work out what those powers are for these different moduluses going from 2 up to 7. So for example, if I pick mod 5, 2 mod 5 is of course just equal to 2. 2 squared is 4, 4 mod 5 is 4. A bit more interesting here, 8 mod 5 is 3, 16 mod 5, well it's 15, so that's going to be 1. 32 mod 5 is 2, that will be 4, 125, so that will be 3. So they're the powers of 2. Then if you could do powers of 3, and what we are looking for is some kind of pattern in the answers that we are getting, because there are some that are particularly significant. And then the bottom one, powers of your choice. So maybe don't go for 127. Stick to smaller numbers, but just pick a different number. You can, of course, if, for example, when it comes to working out 2,187 mod 6, for example, use your calculator. And I have since checked, before I started today, where it is, where the mod button is. You go to Option, F6, the arrow, Numeric, F6, the arrow, and there it is, mod. So if I wanted to type in, and I don't even need the 2,187, I could just type in 3 to the power of 7, and I want to work that out. Mod, comma, mod 6. There you go, it's told me that that answer is 3. So I could pop that in there. Okay, so pause the video and work out a few residues. Okay, so hopefully you got these answers for 2. And there are some in particular that I have highlighted. So if we look on these diagonals here, it's almost, well, it's not almost all a 2. There's a 4 and the 0 there. There are some other kind of 2s floating around in different places. But what we're doing is we're looking at common themes, and now we can see on this 3 page that there are a few 3s on that leading diagonal as well. Is it the leading diagonal? No, I think strictly that one would be, but on this diagonal. There are a few 3s that I haven't highlighted, but there's something significant about these green ones there and these green ones there. So let's look at the powers of 2 first of all. This one here, what that's telling me is that 2 cubed is congruent to 2 mod 3. This one here, that's telling me that 2 to the power of 5 is congruent to 2 mod 5. This one here, 2 to the power of 7 is congruent to mod 7. This one here doesn't fit the pattern, does it? So 2 to the power of 6 mod 6 actually is equal to 4. Here, 2 to the power of 4 mod 4 is equal to 0. This one I've highlighted in green, and I've highlighted that one in green because, of course, 0 mod 2 is congruent to 2 mod 2. So 2 squared is equal to 4. It's congruent to 0 mod 2, but in particular it's congruent to 2 mod 2. We can, of course, further simplify that. So what I seem to have is 2 mod 2, a 2 mod 2, a 2 mod 2, and a 2 mod 2 for those specific ones. If I look at the 3s and check out that pattern, I've got, well, I've certainly got, let's put the 2s next to it. So I've certainly got these 3s here. So again, I can say, I mean, it's a direct comparison to here. I've got 3 to the power of 7 is congruent to 3 mod 7. And there I've got that 3 to the power of 5 is congruent to 3 mod 5. I do have a 3 there. I had a 4 there, so it seems to fit with the 3s, but it didn't fit with the 2s. There I have a 0 and a 1, so I appear to be having 2 different values here. What have I done here? I've also kind of highlighted those, but it's a 0 and a 1. They, of course, also fit the pattern in a similar way to this 2 mod 2 fit here. This one, 3 squared, 3 cubed rather, is equal to 27. And 27 is congruent to 3 mod 3. It, of course, is congruent to 1 as well, but it's congruent to 3. So what we're looking for is we're trying to, you know, note that pattern of getting 3 here. There I have got, what is it, 3 squared. 3 squared is equal to 9, and 9 is congruent to 3 mod 3. So again, I've got that 3 appearing there. I don't know what mystery value you chose. I chose a mystery value of 10 just because it made the powers easy to work out. I don't have any 10s in these same corners. So what I seem to be doing each time, I'm highlighting that one, missing one, that one, missing one, that one. That one, miss one, that one, miss one, that one. So again, I've highlighted these same ones in green. Do they fit? Well, here I've got mod 2. 10 squared is 100, and of course that's congruent to 2 mod 2. This one here, 10 cubed is equal to 1,000, and of course 9999 is congruent to 1 mod 3, but it's also, that's congruent to 1 mod 3, but 1 mod 3 is congruent to 10 mod 3. And looking back at that, that's not particularly useful, is it? 2 is congruent to 10 mod 2. I want the kind of 10s appearing here because I'm dealing with powers of 10. Here, what was this one? This was 10 to the power of 5. 10 to the power of 5 is a few zeros there. And of course, that's congruent to 10 mod 5. And this, you know, similarly, however many zeros that is, whatever that number is, that's going to be congruent. 3 mod 10 is congruent to 10 mod 7. Sorry. 3 mod 7 is congruent to 10 mod 7. So I've got these things appearing here, and you can probably see below here, all of those green ones suggests that whatever my number is here, if I raise it to a prime power, it's congruent to that original number mod p. And you probably spotted the prime, the way I kind of was missing this and missing this every time. So the result seems to work every time for 2, 3, 5 and 7. So if we go back to these two here, get 2, 3, 5, 7. And this is my power of 3. I've got 2, 3, 5 and 7. So there were other threes, for example, appearing in other places, but it's a consistent result whenever we have got a prime modulus. We always have this result. And note the value itself, so the base doesn't have to be prime. So what we had here, we had a 10 going in there, didn't we? We had a 10. That value doesn't have to be prime, but the power and the modulus have to be prime. Now I've also highlighted some in yellow. The ones in yellow, they're all congruent to 1, but look at when that happens. That happens, so if I start this one here, a power of 7, a power of 5 and a power of 3. These ones here happen for 7, 5 and 1. So they're not the same, are they? They're not the same in every one. But what we can say is that that one there, that 3 and that power of 2 there, they're 1 apart. Here I've got a 5 with a 4. They're 1 apart. So the powers themselves aren't prime. So there I've got a power of 6, but they're 1 apart from each of the moduli there. So we would, or we could say that is 2 to the power of 3 minus 1 is congruent to 1, and we're dealing with modulus of 3. This one here, we would say that 2 to the power of 5 minus 1 is congruent to 1 mod 5. That one there, 2 to the power of 7 minus 1 is congruent to 1 mod 7. Okay, so we seem to have that connection. It's 1 step apart. If you look at the powers of 3, I've got 7 matching with 6. So 3 to the power of 7 minus 1 is congruent to 1 mod 7. There I've got the connection with 5 and 4. Doesn't work for this one, mind. It doesn't work for when I've got mod 3 and that 3 squared happening. It works for this one. So we seem to have that sometimes we've got this connection, and I've got my powers of 10 here, and I've also just highlighted 2 here. So there's only 2 1s along this diagonal here, and those ones are for 10 to the power of 3 minus 1 is congruent to 1 mod 3, and that one there, 10 to the power of 7 minus 1 is congruent to 1 mod 7. So as I said here, this purple suggests that sometimes A, again, it doesn't matter what the base number is, so it can be 10, that doesn't have to be prime, but we only ever seem to get the 1s appearing when we've got prime rows. So A to the power of p minus 1 is sometimes, most of the time, congruent to 1 mod p. And it's failing for these ones here. And you might kind of note a connection between these. You also might think, well, essentially, these, of course, are just the same thing. Remember, we can divide. It's certainly the first method we looked at solving congruences. If you have a 2x there, we can divide both sides by 2 as long as that 2 together with that value in there are co-prime. If you can state that A and P are co-prime, then of course you can divide by one of those factors of A. They are essentially the same thing. So suggests that sometimes, and that sometimes is when the HCF of A and P is equal to 1. So that is a condition that we need to go with the purple one. It, however, seems to work every time with the green one. Now, this is known, these two results here are known as Fermat's little theorem. You probably recognise the name Fermat. He's got a more famous last theorem. And it's called his last theorem because it was the last one to be proven, and it was actually kind of over 300 years for this theorem to be proved when I was at university doing my maths, which was quite exciting. So Fermat's last theorem looks a bit like Pythagoras, only it's got higher powers. I'm sure many of you have heard of this. But what he said was that there are integer solutions for x squared plus y squared is z squared, which is essentially Pythagoras, but there are no integer solutions for any power higher than 2. So x to the power 4 plus y to the power 4 equals z to the power 4. There are no whole number solutions. And he was writing just kind of little scribbly notes in essentially a maths textbook. So this was kind of stated as a fact. And Fermat famously wrote, "I discovered a truly remarkable proof which this margin is too small to contain." And ever since then, people were trying to prove this result. And it was done by really quite modern maths. So people think that Fermat actually made a mistake with his proof. This one, he wrote a letter to one of his friends back in 1640. There he is. There's the original French. I'm not going to read that out for you. There is a translation of it. The language is a little bit complicated. The things in brackets are just added to put it into notation. Every prime number divides one of the powers minus 1. So, of course, that's kind of looking at that there. And the exponent of this power divides the given prime minus 1 after one has found the first power that satisfies the question. So if you read through, you've got to do a little bit of translating, even just to get it into algebraic form from the English translation, let alone the original maths. But the quite kind of amusing thing is, particularly after his margin comment for Fermat's last theorem, again he didn't prove it. He said, "And this proposition is generally true for all series and for all prime numbers. I would send you a demonstration of it if I did not fear going on for too long. I am sure we would all like to write that whenever asked to prove something by induction. Oh no, it would go on too long. It would be nice, wouldn't it, to state that." The proof, first published by Leonhard Euler, another mathematician that you will have heard about lots. Particular complex numbers, you're going to do some fantastic things that he came up with Mrs. James in Pure Core 2. But again, this other mathematician, Leibniz, he's done a few things that then other people got credit for. So in particular, calculus, Newton is known as the father of calculus. However, Leibniz was working on it around about the same time, and actually we use his notation as well. The proof we're going to look at in tomorrow's lesson. What we are going to do is we are just going to be using these two theorems, or these two versions of the theorem. This one is the one that tends to get used the most. It's certainly the most useful. And I've just said again here, encryption via the internet, whenever you see that little lock key, they are using prime numbers. They're using huge prime numbers and relying on people not being able to factor these prime numbers. Okay, so everything we've done so far has basically just been introduction. Some of you might call it waffle, but I think it's all quite exciting stuff. Here are two theorems again. So if you're doing kind of official notes, I would start at this point here. You may just have printed everything off. I'm going to start off just with a couple of illustrations. So rather than, I haven't really called these examples, but first one here. So we're going to choose 5 for our prime. And as I said, this is the version that tends to get used the most, so I'm going to be looking at that one for each of these. So Fermat's last, sorry, I keep saying last, it's his little one. 3 to the power of p is 5, so 5 minus 1 is congruent to 1 mod 5. So 3 to the power of 4 is congruent to 1 mod 5. That's what Fermat's little theorem says. Let's just have a little look and check. 3 to the power of 4, 81. And 81, of course, is 1 above a multiple of 5. Yep, so that works as we'd expect. And we knew that was going to work because the conditions we got up there, we've got to have p being a prime, as 5 is a prime, and the HCF of A and P, so this is going to be 3 and 5 is equal to 1. So whenever you use Fermat's little theorem, you have to state the conditions. Right, I've got this, so it's okay to use it. They're happy for you to use FLT as an abbreviation. So here, A is equal to 8. Note, again, that base doesn't need to be prime itself. What Fermat's little theorem says is that 8 to the power of 5 minus 1 is congruent to 1 mod 5. Or 8 to the power of 4 is congruent to 1 mod 5. 8 to the power of 4, that's 4096, and again we can see that's 1 above a multiple of 5. So yeah, but I knew that was going to work because I knew that as 5 is prime and HCF of 8 and 5 is 1, then I know I can use Fermat's little theorem. The last one, oh, okay. Well, let's see what happens when A is equal to 10. Some of you are hopefully thinking, oh, hang on. I'm just going to plough on. 10 to the power of 5 minus 1, 10 to the power of 4 is congruent to 1 mod 5. Oh, but hang on, no, of course that doesn't work. Because 10 to the power of 4, of course, that's a multiple of 5. So the reason, sorry, that's a divide symbol, so but 5 divides 10,000. So the reason that that didn't work, so 5 is prime, but the HCF of my base 10 and that prime is not equal to 1. So Fermat's last theorem does not apply. Okay, so whenever we are looking at Fermat's last theorem, all we need to do is just state down those conditions. If you have got this going on, we can't use it. So if you're asked a question about it, there should hopefully be some other technique that you can use. Okay, so start of all of that, getting to this point, it's been quite lengthy, but the rest of this session, it's just talking through, I think I've got 4 or 5 examples. Certainly start with fairly basic applications of Fermat's little theorem. So this one here, I've got a prime number, I need to say that. So as 11 is prime, and I'm interested in the highest common factor of 511, that's equal to 1, then we can apply Fermat's little theorem. Okay, you have to say that. So, I mean, for the first couple, I know I'm doing it a little bit more lengthy than you may want to. So I'm writing down Fermat's little theorem with A is 5 and P is 11. Then that will give 5 to the power of 11 minus 1 is congruent to 1 mod 11, or 5 to the power of 10 is congruent to 1 mod 11. Of course, it is a show that, so we have to put a little bit more writing than we would like to. Oh, it's obvious, but we still need to write those steps down as it's a show that. Okay, right. Another show that. This time we are looking at that unsettlingly large number being congruent to 1 mod 13. Right, we have got a prime number there, and if you think about what Fermat's little theorem says, a to the power of p minus 1 being congruent to 1 mod p. Okay, so our prime is 13. So because of that, even though, you know, I've got this kind of quite big number there, we know that we are looking for a power of p minus 1. So looking for a power of 12. And 4096 really isn't that kind of big, particularly when you're dealing with powers of things. So there's only going to be one thing that fits the bill. It has to be 12. Sorry, it has to be 2. It has to be 2 to the power of 12. 2 to the power of 12 is 4096. So I would note that 4096 is equal to 2 to the power of 12, which is 2 to the power of 13 minus 1. So I would be looking at something with A equaling 2, P equaling 13, they are co-prime. So as 13 is prime, and HCF of 2 and 13 is equal to 1, I can say that by Fermat's little theorem, 2 to the power of 12 is congruent to 1 mod 13. It's a show that, I mean, I know I've kind of essentially spelt it out. It's a show that, so we need to finish on that line. 4096 is congruent to 1 mod 13. Okay, I think that is the last of the show that, so that means that we can just kind of, you know, work the thing out and not have to worry about have I written enough down to get me those marks. So 3 to the power of 31 mod 7. I'm not sure actually, is my calculator able to take that? So modulus 3 to the power of 31, comma 7, out of domain. Okay, so calculator can't help. Certainly not at this stage. That power of 31, well, that doesn't really fit the 7 minus 1, does it? But as I've got a prime number, and the base certainly fits the condition, then let's write down what Fermat's last theorem tells us. Fermat's last theorem would tell us that 3 to the power of 6 is congruent to 1 mod 7. So I know that 3 to the power of 6 is congruent to 1 mod 7, but I somehow need to translate that into 3 to the power of 31. So what we do is we think, how can I write 3 to the power of 31 in terms of 3 to the power of 6? And 3 to the power of 31 is equal to 3 to the power of 6 all to the power of 5. That, of course, gives me 3 to the power of 30, and I've got an extra power of 1. Now, it's, you know, kind of just obvious, but there is, you know, a power rule that you would have done with Mrs. James when you looked at number theory earlier this year. If we know that A is congruent to B mod n, then essentially it's just a special kind of multiplication, isn't it? Use a different letter. Then A raised to some power is congruent to B raised to that same power in that modulus. So what we can say is we can use that to help us work out that. It means that as we know that 3 to the power of 6 is congruent to 1 mod 7, then 3 to the power of 6 all to the power of 5. So this is in place of the k, of course. So I've got that k, 5. I'm going to have a 1 to the power of 5 mod 7. So 3 to the power of 30 is also going to be congruent to 1. 1 to the power of 5 is, of course, equal to 1. So if I take it back to our 3 to the power of 31, 3 to the power of 31 is equal to 3 to the power of 6 all to the power of 5 times by 3. That is congruent to 1 to the power of 5. That bit, I've still got the 3 mod 7. Sorry, that is a power of 5. Looks a bit like a 15. So it's 3 mod 7. Okay, so think how you can connect that. It's very unlikely that you'll have something, you know, just as convenient as that p minus 1 there. More often the questions are you have to do this little adjustment with the powers. Okay, so a couple more. Find the remainder when you divide 29 to the power of 25 by 11. Of course, this is asking us to find 29 to the power of 25 mod 11. The first thing we can do is think about that 29. Okay, so I know it's attached to a power, but still if you were faced with 29 mod 11, you would just say, oh, right, I can subtract 22, and that is congruent to 7 mod 11. So what we can say now is deal with the power. So hence I've got 29 to the power of 25 mod 11, and that is congruent to 7 mod 11. I haven't got the power of 25. Sorry, put that in. We have our conditions right for Fermat's little theorem. So I've got a prime number, is 11 is prime, and HCF of 7 and 11 is equal to 1. Then by Fermat's little theorem, I can say that 7 to the power of 11 minus 1, so 7 to the power of 10, is congruent to 1 mod 11. We've got a power of 25, so 7 to the power of 25 is equal to 7 to the power of 10 all squared. That gets me a power of 20. I need an extra power of 5. So that is congruent to 1 squared times by 7 to the power of 5 mod 11. Now, this 7 to the power of 5, we could just work it out on our calculator. So mod 7 to the power of 5, I am assuming that this will fit in my calculator, comma 11, be okay, told us it's 10. So that's congruent to 10 mod 11. You might just going to want to write in what that is equal to. So 7 to the power of 5. No, I've done to the power of 4. Sorry, just pressed it lots of times. 16,807. But you might just want to, you know, pretend you were back when they first were doing number theory. How would we have dealt with that 7 to the power of 5? Well, one thing we could do, so you can leave it there, but one thing we could do, that 7 to the power of 5 is equal to 7 times by 7 to the power of 4 mod 11. Seems a bit random, but 7 mod 11 is congruent to minus 4. And of course, you know your powers of 4. You know your powers of 4 because you know your powers of 2. Powers of 2 are straightforward. 64 is 2 to the power of 6. So 128 is 2 to the power of 7. 256 is 2 to the power of 8. 2 to the power of 8 is 4 to the power of 4. So that is 7 times by 256 mod 11. And I think I can divide that by 11 because I know that 220 is. So 242 is, so 253 is. So that's congruent to 7 times by 3 mod 11, which is congruent to 21 mod 11, which is congruent to 10 mod 11. Okay, so of course, I mean, up until not very long ago, you wouldn't have been able to, you certainly wouldn't have a modulus key on your calculator, and you'd have to work it out using those methods. Okay, last one for today is 7 to the power of 329 mod 50. Okay, so it's one where we've got a really big power, but actually there's a more pressing problem here. We have got not a prime number. So here, Fermat's little theorem doesn't help, as 50 is not prime. So you may have been asked this last year. We have to just stick with year 12 methods. Now, it's a clever question, but it's kind of a little trick, and it only really happens with 7 and mod 50. I don't know whether you can spot why. There's something in particular that connects 7 to 50. And the key fact here that's going to help us is that 7 squared is equal to 49. That's only 1 away from the 50. So we can write 7 to the power of 329 as 7 squared. It's going to be 164. That will get us to 328 times by an extra 7. So that's equal to 49 to the power of 164 times by 7. And now we can say that because we're dealing in mod 50, that bit's congruent to -1. That bit's congruent to -1. -1 to the power of 164 is equal to 1. 1 times 7. So I have got 7 mod 50. And it does, you know, it feels as if that's kind of fitting, doesn't it, with our Fermat's little theorem, in particular with this one here, because it's 329 prime. I'm actually not very sure, but well, of course that doesn't match with that, but it kind of, you know, looks a bit like that anyway, but it only happens with the 7 in particular, because 7 is just 1 away. I'm sure there are other things where you've got, you know, other powers that are 1 away from what your modulus is. Have a go at these questions. So these questions, you know, hopefully they're not too kind of tricky, just numerical. It's just a matter of playing around with Fermat's little theorem, wondering how you deal with these bigger powers. Oh, look, there's a 7 and a 50, not prime, but it's fine. And they're just, you know, quite a big number at the end.